look at the following pictures. The one on the left has a pizza, or a box of pizza, and a collection of perfume or cologne. The one on the right are balloons that shows the before and after effect. Now, choose between these two group of images which is diffusion and which is effusion. Right. If you said that the boxes or the images here on the left is or has something to do with diffusion, and if you said that the box here on the right has something to do with effusion, then you are correct. Do you still remember that when you are in an air-conditioned room and then one of your classmates entered with a box of pizza? Isn't it that you can smell the pizza even if it is inside the box? And same goes with the perfume or cologne. When someone sprays cologne or perfume, okay, even if that person is 3 or 5 meters away from you, after some time you can smell his or her cologne. Now, the reason for that is because of the movements of the gases. Now, when we say diffusion, this has something to do with the movement of gas molecules from a greater concentration to lower concentration. For effusion, okay, now look at the pictures here. This is the before and after. The red balloon is filled with helium gas. The blue balloon is filled with hydrogen gas. And then the green balloon is filled with an oxygen gas. The balloon that is filled with oxygen is still the same, right? Now, this has something to do with effusion. What is an effusion? So, an effusion is through a process by which the gas escapes from its container through a tiny hole into an evacuated space. So, let me show you an example again. Helium-filled balloon. It's inside. Now, the reason why it shrunk, is because it's too small that it can escape the wall of the rubber balloon, and this is called an effusion. Okay, it is where the molecules of gases escape through a tiny or a very small hole, okay, from a greater concentration going to the lower concentration. So again, diffusion has something to do with the movements of the molecules from a greater concentration to a lower concentration until the entire place has an equal amount of distribution of the gas molecules. And effusion, okay, again, this is a process of which the gas escapes from a tiny hole, maliit na butas, okay, going through an evacuated space. Now, Thomas Graham, who formulated the Graham's law of effusion, states that the effusion rate is inversely proportional to the square root of gas's smaller mass. So, sabi niya, yung rate of effusion, let me write it down. The rate of effusion is inversely proportional, okay, to the square root of the molar mass of the gas. And that formula can be written as rate of gas A, or gas number 1, over by the rate of gas B is equals to the square root of the molar mass of molecule or gas B over by the molar mass of gas A. Now, this rate pertains to the molar mass of this gas. Okay? And the rate of B pertains to the molar mass of B. So, do you remember the kinetic energy that we've discussed before? If the gases here are moving at the same temperature, therefore the kinetic energy is like this. Let me just copy this. Then I'm gonna post it here
6 months later.
so that you can see it.
Meanwhile, a few moments later.
Again, the relationship of rate A or the gas A with mass A and rate B with mass B can be taken from the kinetic energy if they are in the same temperature. So this will be cancelled out. Same with the other halves. So we now have m sub 1 v sub 1 squared is equals to m sub 2 v sub 2 squared. Now we want to isolate the velocity or the speed. So it becomes v1 squared over by v2 squared is equals to m2 over by m1. Now we want to remove the squared in velocity, so let us like this so that we can remove the root symbol. So now what we have now is, let me write it here. So we have v1 over by v sub 2 is equals to the square root of m sub 2 over by m sub 1. Now the similarity is really visible this time, right? So we can say that this is just a simple application of a Newtonian concept. Now, when solving the effusion rate, you have to consider the following steps. So the first one is to identify the molar mass of the given elements, right? Then the second is to identify or set rates. And then number 3 is solve using the Graham's law of effusion. Okay? So let us have an example. So let's say this is our example number 1. Let us say we want to find out the effusion rate for helium and neon. So what is the ratio of effusion, right? Effusion rates or the effusion rates for helium and neon. Okay, so then what is the ratio of effusion rates for helium and neon? Alright, so before we solve this problem, let us remember the 3. Identify the molar mass, set rates, and then applying Graham's law. Going back to the problem, okay, so what is number 1? Is identify the molar masses of the elements. So what are the elements involved? We have helium and also neon. Now we can check the periodic table to see their molar mass. Okay, alright, so this is the periodic table. So let's check on helium. And neon has a molar mass of 20.19. So the molar mass for helium is 4.003, that's gram per mole. And for neon is 20 point, what's that again? 20.18, right? 20.18 gram per mole. So this is the first step, which is identify the molar mass of the given gases. Okay. Now the second one, or the second step, is we have to set the rates. Right. So let our rate A be helium, and let our rate B as neon. And then the third step is to solve using the Graham's law of diffusion. Okay, so we have rate A, which is helium, over by rate B, which is neon. Okay, so helium and neon, which is equals to the square root of the molecular mass of neon over by the molecular mass of helium, which is equals to square root of that's 20.18 over by 4.003, and that will give us, wait, let me solve it.
One eternity later. Much later.
Right, and that gives us 2.2. Okay. Helium effuses at a rate of 2.2 that of neon. Alright, example number 2. What is the rate of effusion of oxygen gas compared to hydrogen gas? Okay, so let us not forget the step. First step is to set the molar mass. Okay, let's identify the molar mass of the given gases. We have oxygen and hydrogen. So, molar mass of oxygen gas, and then the molar mass of hydrogen gas. Notice that I write here a subscript 2 because by nature, oxygen gas is diatomic. Same with hydrogen gas. So, both of them are diatomic. What do you mean by diatomic? Oxygen atom exists with another oxygen atom. Okay? Same with hydrogen atom, it exists with another hydrogen atom. So, lagi silang dalawahan. That's why they are called diatomic molecules. Okay? Diatomic. So, be careful. When you look at the periodic table, you will see hydrogen here having a 1 atomic mass, and then oxygen is 16 here, right? Now, if you identify the molar mass of oxygen as 16, okay, it will be wrong because there are two oxygen atom that represents the oxygen gas given here. Same goes with the hydrogen gas because they are diatomic. Okay, because they are diatomic. So, what can we do? Let me just erase this. Okay. So, that will be the atomic weight of oxygen is 16 times 2 because there are 2 atoms in an oxygen gas. That gives us 32. Okay, and then for hydrogen, the atomic mass of hydrogen is 1, and also there are 2, So it is 2. Right? The second step is let us set the rates. Let rate A be our oxygen gas. Okay, and our rate B is the hydrogen gas. Okay, again, this is our rate A, and this is our rate B. So, oxygen and hydrogen. So, let's now go to the third step, applying the Graham's law of effusion. So, rate A, which is oxygen, okay, and then rate B is hydrogen, is equals to the square root of molar mass of hydrogen over by the molar mass of oxygen. And this gives us 2 over 32 square root is equals 0.95. The computed value tells us that oxygen gas, okay, moves slowly 1/4 times compared to hydrogen gas. Okay, actually we can predict it that the oxygen will move slower compared to the hydrogen gas because of their molecular mass. You remember that when we talk about the relationship of the speed and mass, the more mass, okay, a molecule has, the tendency is it will move slower. Okay, this is going to be the slow. Okay, the more mass it has, it will move slow. The lesser mass, of course, the faster it will move. Okay, so you can predict it before you mathematically prove it, right? So again, this value tells us that oxygen gas moves 1/4 times slower than the hydrogen gas.